So before the break, we stopped with this picture, which is, well, it's an ugly picture, but the concept it represents is somewhat pretty one. There should be a sort of correspondence between structural properties on this automata and some arithmetic properties on the functions that they realize. And, well, we cannot turn everything around, but at least some things we can also already turn around. And sort of there's this at least conjectural picture that hopefully eventually we can turn everything around. Modulo mistakes. And what I want to talk about now is this unambigualizable case. So here, every non-zero value of your function was a product of some finitely many fixed values. And we claim that then there's an unambiguous automaton that recognizes it. And determinizable will then fall out as a subcase. And then I claim, and hopefully I will at least be able to indicate a little bit, that the way we do this construction, it then actually gives rise to an algorithm if you do a lot more work. Okay. So what I want to tell you about the two main tools we use here. And the first is the so-called linear hull, and more specifically the associated linear hull automaton. I should maybe not say there, but add, because this is not completely unique. And the second one is deep theorem from Diophantine number 3. These are the unit equations. This is basically about solving linear equations in a finitely generated subgroup of a field. You might also see it sometimes as S-unit equations. The S doesn't make so much sense in this context, but this is where the origin is in algebraic number theory. This was a finitely generated subset of a number field. Multiplicative subset. And I want to focus on this point first. The linear hull automaton. And what I'm going to say is in some sense true over every field, but to make some simplifications, I will just look at fields of characteristic 0. So really, let's just look at rational numbers. It doesn't, everything interesting already happens there. And let's look back at this example that we had here for a moment. I mentioned this reachability set omega. What was this? We have our initial vector u somewhere, and then we apply this anti-matrix semigroup on the right. So we look at this orbit. This was u star. And I said in general membership in this set is not decidable. Let's look, for instance, what happens here. So I start with 1, 1, 1, and I apply powers of a from the right. So I'm getting all vectors of the form 2 to the n minus 2 to the n, 3 to the n. Okay. But of course, that's not everything. Now I could apply C. So C is just going to kill the first two entries, and it's going to multiply the third one by 5. So I'm getting vectors of the form 0, 0, 3 to the n, 5 to the m, and so on. Well, what does B do, for instance? It copies the third entry into the first two ones, and it might and it sends the second one into the third one. So if I multiply this, no, this is not what okay, I want to multiply this, the first one by some powers of p, and then I get 3 to the n, 3 to the n, say, and then minus 2 to the n. Okay. And then I can again multiply by some c and b and a and whatever, and I get a fairly complicated set. What seems to be true here is that the first coordinate is always plus or minus the second one. So there's a sort of linear invariant. And this is something that I want to capture now with the linear hull. It's not completely clear at this point why we want that, but this is going to work. Okay, so how to capture this abstractly? We're given some finite dimensional vector space V. And in our case, it would just be the row space over K. More generally, we also think of the matrices as a vector space if you want to do this later for the matrix semigroup then. And okay, we call a subset Y in V closed if it has a particular shape, if it is a union of finitely many subvector spaces. So if and only if, by definition, Y has a representation of this form, W1 union up to some WL, and these WI's are subspaces, subvector spaces. Okay, I call it closed because you could check these are the closed sets of a topology. So they are closed under arbitrary intersections, under finite unions. The empty set is in there, the other space is in there, but we won't really need that here. But we call this thing the linear heuristic topology. Okay. And now some relatively easy facts that we're not going to prove. So first, if you represent Y in such a way as a union of finitely many subspaces, this is essentially unique. Of course, what you can do is you can permute the spaces, and it could be that one is completely included in another, but then you just drop the one that's included. So if you have an irredundant representation, it's unique. So let's call this star. This representation star of Y is unique if, well, some Wi is not included in Wj if I is not included in J. So drop redundancy, we get something unique. And the underlying reason for that is quite simply that if you have a, so we have a field of characteristic 0, so in particular it's an infinite field, and then if I have a vector space, I cannot cover it with finitely many proper subspaces. So if you have some plane in R3, for instance, there is no way you can cover it with finitely many lines. And similar, if you have a 3 space, you cannot cover it with finitely many planes and lines, right? And this would show you then, if you check a little bit, that if you have some other representation, and then let's say you have some W prime that is included in a union, it must already be included in one of them. So no vector space is a union of finitely many proper subspaces. That's the underlying effect. If you know so much rate geometry, this thing behaves like this heuristic topology. Okay, and these are the irreducible components. But you don't need to.
Excuse me, I kind of get the set. How Y is defined? Is that any set which is closed?
Yeah, so we call a set of a subset of V is called closed if it has this representation. And now we look at the collection of all closed set.
Okay.
So this is the definition. Yes. There should be a double point here. Now it's a definition. Yeah. So these are the closed sets. These are the ones we're going to be interested in. And they have one other important property which comes down to the same covering property. If you have some subspace W prime that's contained in Y, then it must already be contained in one of these components. So then there exists some I such that W prime is in Wi. Okay. And this means, if you want to be fancy, the Wi's are the irreducible components of this closed set. Nothing I said here is hard to check. Okay. And now with that topology, we go back to our automaton, or more precisely our linear representation, and we define the linear hull. So definition. So let's say U mu V is some automaton. And actually, let's take this minimal to then really get some results. So minimal linear representation. And then I say the linear hull of A is the closure of the reachability set in this topology. Is U mu X star part. So what you're taking is you take this reachability set and you're looking at all the closed sets that contain it and you intersect them then you get the smallest closed set that contains them. This is the closure. Okay? And now the reachability set is a complex structure, but the closure by definition, it's just a union of finitely many vector spaces. So this is a finite representation. Of course, it's a different story to find it, and this is going to be the hard part of the algorithmic thing. But as an object, it's simple. Maybe one small comment. We're doing this from the left. So it's the left linear hull. You could do it from the right when you fix V here. You're also getting something. And it's going to be in general different. This corresponds to the fact that, for instance, WA can be determinizable when you read words from left to right, but not the other way around. Okay? But we just always do it from the left. And now, if you were to go back to this picture, determinizable means the reachability set for a minimal automaton is coverable by finitely many lines. So really, in this new abstraction, it just says all the components of the linear hull are one-dimensional. So a minimal linear representation is determinizable if and only if the linear hull is one-dimensional. Okay? So you cover with this new notion a simple statement of this old fact. And this gives you a first idea that this is maybe a nice invariant for automaton. Okay, let's look back at our example. And maybe I clear this picture here now.
This closure is invariant under each step, each transition of automaton, right?
Exactly, yes. If you multiply this on the right by one of these transition matrices, you're staying in omega, therefore you're staying in omega bar. Okay, let's look at this thing. We noticed before that it seems the first component is always plus or minus the second component. So we can make a guess at least what this linear hull is. So we're looking sort of for the smallest union of finite vector space that covers this. So our guess would be that, say, this means E1 plus E2, E3, so spanned by this sum of the first two standard basis vectors. This is the first and second coordinate equal, and the third one is independent. Or you have E1 minus E2 and E3. So this is a union of two planes. And our guess would be that this could be the linear hull. You can also write it, somehow maybe this is easier to see then. Let's write it as like x, x, y, union x minus x, y. These are claimed on the two components. Well, how would you check this? You would check that this set actually contains the reachability set. This is quite easy. So the starting vector u is in there. This is just 1, 1, 1. This is in here. Well, and now all the other vectors in my set omega are generated by applying these three matrices. So I could just check that this entire set is closed under these matrices. And indeed it is.
May I have a stupid question? Because if I would take a very simple automaton which has only one letter and multiplying by 2 always, like on a loop.
Yeah.
Okay? Then no.
The linear hull is the entire one-dimensional space. It's a line.
Yeah, so you are not observing this kind of exponential growth. There is no interdependency between length and.
This is not about growth. This is about the multiplicative structure of the outputs. They can grow exponentially. Yes. So growth is not at all detected by this.
So am I correct that in this case the linear hull will be two-dimensional, therefore this is not determinizable?
Yes. But maybe I should say this. If you play around with this example a little bit, you will see that you only get numbers whose prime factors are 2, 3, and 5, I think, maybe. I don't know. Yeah, 5 should also come up. So according to our not so nice picture, this thing should have an equivalent unambiguous automaton that recognizes it. But this one is obviously not, because we already saw in AB, you're adding 2 rungs. So what we're trying to do now in this example is we're constructing the one unambiguous automaton that recognizes this solution. And the first step is to figure out what this linear hull is. Well, and let's call these components W1 and W2. So in W1, the first and the second coordinate are equal. If you multiply on the right by A, well, it's going to switch the sign of the second coordinate. So it's going to send something from here to here. So you just have to actually check this on the basis vector. So E1 plus E2 of A is going to be 2E1 minus 2E2, and this is in W2. Okay, and if you do this properly, you will see the following. A sends something from W1 into W2, and conversely. So we can record this as a sort of automaton. And my initial state U, it's in W1. Now if you do this for B, so B always copies the third state into the first and the second one. So they will have the same sign. So whatever you apply B to, you're going to land in W1. So if you start from W1 and do B, you are here. If you start from W2 and you do B, you're here. So what's C doing? Well, it kills the first 2 entries, and it multiplies the set one by a scalar. So it's just going to give you a multiple of E3 that is in both sets. So you could now write this as a sort of NFA, like C goes here, C goes here, and also sort of C goes here. And I make this dotted because I'm just going to drop these. So there's going to be a choice in a moment. But what we see from this picture at least is that this set is invariant under multiplications on the right by ABC. So if you start with the vector U that's in there, its orbit is also going to stay in there. So certainly this is a closed set that contains the reachability set. Okay. To be the closure, it should be minimal. So you want density. You don't want to be able to replace one of these planes by finitely many lines that still cover the whole thing. And now you look a bit closer here. Well, so basically, if you look at the orbit here, you realize that between the first and the second coordinate, in each of these components, you will get infinitely many ratios, which would contradict this being covered by finitely many lines. So you can sort of manually, in this example, check that this is really the linear hull. It's doable by hand, but you see, algorithmically, this is going to be the difficult step. Okay? But then once we have the linear hull, we have a nice representation, I think. And now we want to make an automaton out of this. So where do we do this here? No. It's the linear hull automaton. I wanted to recognize the same series. But it's going to have more states. It's going to be defined on a larger space. And so this automaton is going to be called A hat. And the space I take these components of the linear hull, and I make the external direct sum. So here I have 2 planes in 3-dimensional space, and they intersect in a line. I make an external direct sum of these things. So they don't intersect anymore. I have 2 planes in 4-dimensional space. So I define my new vector space V hat, let's say, as W1 external direct sum W2. So elements are pairs of elements from W1 and W2. This is 4-dimensional in the example. Okay, that's a nice vector space, but now we need to define some more an automaton on this, which means we need to see what the matrices for each letter do. Okay, and each letter, let's say mu x, well, the matrix, it's a linear map essentially on the vector space where V was K1 cross D. Okay. These were my original ones. And these WIs, well, they are subspaces of the original space. To see what it does on what it should do on W hat, I want to sort of explain what it does on this direct sum. For that, it's enough to say what it does on each of the components, and then it's the sum. Okay, so I need to know what does mu of x do on W1, what does it do on W2. Well, so we restrict it. Let's say mu of x restricted to Wi. This is going to go, well, first it just goes from Wi to V. That's at this point not super useful for me. But I know this is going to stay in the linear hull. You cannot see. Should I switch? Let's try this. Better? Okay, sorry about that. Okay, so this goes to V, but actually it goes to omega bar, which is the union of these vector spaces. In general, it will go up to some WL. In the example, there are just two. Now, I could be kind of screwed, but I'm not, because I know the image of Wi on the linear map. It's a linear subspace, so it's going to be contained in one of these things. It might be in the section of multiple, but there's at least one that contains it. So there exists some J, so that if I, well, I applied on the right. If I apply to Wi mu of x, I'm going to land in Wj. And which one it is exactly this. This is told by this graph. For C, I have two choices. I land in the intersection, and I'm just making the choice. I say, okay, I want my mu C to map W2 into W2 and W1 into W1. So there's a non-canonical choice there. So I choose, so I encode this with a function f. So for each letter and each of my components of the linear hull, 1 through L, it tells me which component this letter should map into. So this is going to go to 1 through L, such that if I start with Wi and I apply the letter x, I'm going to land in Wi f of x. Okay? Good?
So you choose one.
I choose one if there are multiple choices. Yes. And this, in my example, this only happens for C. And it doesn't matter which choice I make. Okay, but now I can define on this bigger space corresponding matrices with a certain block structure. I know that A should go from W1 to W2 here, and now I look what the matrix actually should be doing. So let me swap boards. Okay, so how do we define these things? Well, to write things as matrices, we choose bases on our spaces. And I'm just going to take these vectors as bases. So on W1, this was E1 plus E2 and E3. And I'm choosing my bigger space a new basis where this E1, E2 will sort of, well, it's not really an equality, but it should correspond to E1 prime, to a new basis vector. E3 will be some E2 prime. And then for the W2 component, I have E1 minus E2 and E3. And this E1 minus E2 will correspond to E3 prime. And the E3 here, this lives now in a different space. I've separated this. Is going to be E4 prime. This was a 2. Okay. Now I want to say, what does A prime do? I should apply to one of these vectors, right? To say E1 prime, and it should sort of do the same thing as A. Well, E1 prime was E1 plus E2. I apply A. It's going to give me 2E1 minus 2E2. Well, this is 2 2 times E1 minus E2. So now I want to represent this in my new basis. So this is going to be 2E3 prime. So this tells me if I want to write down A prime, the image of E1 prime is going to be the first column, and it's going to be 0, 0, 2, 0. Okay. Now I keep doing that. Okay, what does, okay, this is actually interesting. What is E3 of A? It should be 3 times E3. But now I want to observe my restriction that I should map from W1 to W2. So I'm starting with the E2 prime, and now in theory I have sort of two choices because the E3 is in both bases, but I want the one in the second one. So I make E2 prime of A prime be E4 prime, which means in a matrix I put, there should be a 3 still, I put this 3 here. Okay. Now you can also do this for these two other vectors, and you're going to get 2, 3, 0, 0. Okay. Do the same thing for the other matrices. We're not going to do it in detail, don't worry. But you see, sort of, if you look at this matrix, this one corresponds to W1, W2, W1, W2. So in this upper right block, you see the stuff that goes from W1 to W2. In the lower left block, you see what goes from W2 to W1, and so on. And B prime, everything is going to W1. So this is going to be 0 on the right side, actually. And then it's going to be here 0, 1, 1, 0. 0, minus 1, 1, 0. So just work it out according to the same thing. And for the C prime, we made the choice that it maps each component to itself, so it's block diagonal, and it will just map, like it will multiply the second vector by 5. So 0, 0, 0, 5 here, there's 0 here, 0 here, 0, 0, 0, 5. Okay? Okay, so far, so good. These are just some instructions on how you write new matrices. We also had sort of our initial vectors, right? U. This was E1 plus E2 plus E3. And we also pick one component that we put it in. In fact, there's only one choice here because it's not in W2, it's in W1. So you represent U in this basis, and it's going to be 1, 1, 0, 0. It's E1 prime plus E2 prime. And now V, V prime, so U prime, V prime. So you see V, it's a column vector, so it's really a function defined on the space. And now, well, you do the same thing as for matrices. You see where does V map these vectors to, right? It's going to map E1 plus E2. It's going to map it to 2. And everything else to 0. So these two vectors also have this sort of block structure. Okay.
Am I right that sometimes if V would be, for example, 0, 0, 1, you can represent it either by 0, 1, 0, 0 or by 0, 0, 0, 1. And this doesn't matter, right?
No, the V, you don't have any choice. You view it as a function on the space, and
let's say it's 0, 0, 1. So when it's in the intersection of W1 and W2, right? So you have to choose whether.
But, well, no. Then it will actually be 0, 1, 0, 1. Otherwise, you would be losing some outputs. Otherwise, when you end up in component W2, you would not get outputs.
Oh.
So for the U, you have a choice, potentially where you start. But this, you should do this instruction really. Apply this thing to the standard basis vectors and see what it gives you.
If it's not in the space, you put 0, 0, and if it is, then you represent it.
Well, I mean, this V doesn't live in the same space, right? It's a column vector, it's in the dual space. So it's really, you should view V as a function from K1 cross D to K. And then you need to ask what is E1 plus E2 times V. So this is applying the function V to this vector, and this you put in the first entry. And then you look at what is E3 times V. This is the second entry, but also the final entry. And then you look at what is E1 minus E2 times V. So this should give 2 if I didn't make a mistake. This would give 0 because the third state is not an output. And this gives also 0 because, so V, the original V was 1, 1, 0. So you're doing 1 minus 1, 0 times 1, 1, 0. But for the V, there's no choice. You would be changing the automaton if you change the V. Okay. Well, okay, we ended up with this U prime, and then mu prime should be the obvious thing. Just mu prime of say, little a is capital A, and so on. So I define this homomorphism. And this gives me a new automaton A prime. And now, we didn't check this in detail, but if you sat down and did this carefully, you would see that this has the same semantics as the original one, always. So at some point, I guess it looks like we just made our life more difficult. But let's, maybe to see something, let's actually draw this as an automaton. Okay. So it now has 4 states corresponding to E1 prime, E2 prime, E3 prime, E4 prime. Let me draw here 1 prime, here a 2 prime, and here 3 prime, 4 prime. And let's draw these boxes to indicate the W1 and W2.
Is it true that by definition this A prime is deterministic or?
No, it's not. You can do this for any automaton and you might end up with something undeterministic. In fact, in the generic case, your reachability set will just be dense in the original space, and you would not do anything really.
But once you've chosen this function F, right, looks like.
But it could be that you just get one component in the closure, right? This is sort of the generic case. If there are no, so what you're doing is you're computing all the linear invariants of the reachability set. If you have some wide matrix semigroup, it doesn't even have to be too wide. So for instance, if you do the Fibonacci thing, you would get the whole 2-dimensional space as the closure. And then then the new space is just the same as the old space. So A prime is going to be equal to A.
Also, so the main property is you preserve the function.
Yeah.
It cannot be always the
Yeah, that's why I asked.
It preserves the function, it's not necessarily deterministic. In this example, it will be unambiguous. I will show you this now. So we have this thing. I'm just going to copy the transitions from the paper. Okay. So the U is U prime is this, these two are initial. And this is terminal with weight 2.
So in this example, it's even deterministic, right?
No.
This matrix
It's two
is
starting
prime,
states.
this prime.
No, it's not deterministic.
You have 2 starting states, you're immediately
Ah,
It's not the one, it's not one.
Okay,
Sorry?
okay.
Yeah, because you start with 2. Yes.
We're starting back
If you dropped 1 here, you would get something deterministic, but it would give you a different series. This one cannot be determinized because the linear hull is 2-dimensional.
Good. But I have the impression that the matrices you produce by this construction are always deterministic.
I don't think it's necessary to. The thing is, often it is the case, especially when they're invertible, it should be, yes. Because they're always semi-monomial. Okay, maybe let me explain this at this point. What does semi-monomial mean? We have this block structure. Look at one row of blocks in a matrix. Say this first row. There's only one non-zero block. Same here. There's one non-zero block. And now look inside one of these blocks. Oh, maybe not this one. Then in each row you have at most one non-zero entry. So this is called semi-monomial. You have on the block level, you have in each row at most one non-zero block, and then if you look inside the blocks, in each column you have at most one non-zero entry. This is what gives you unambiguous, but in general not deterministic. And deterministic is actually also sensitive to the U prime and V prime. So if the matrices are invertible, then you can always make this matrix semigroup deterministic, I think, like monomial. But in general, I don't have an example at hand, but I
So
think
if it's polynomial ambiguous and not finitely ambiguous, it can't be. It can't be. And if you start with something that's polynomial ambiguous, it cannot be finitely ambiguous. Then you necessarily have another.
No, I think we're talking about the case when it's unambiguousable. So otherwise, yes, you're right. Then of course it fails. If it's not possible at all, then this is not going to be unambiguous. Deterministic. Okay, where was it? Okay, so we don't have this automata. Now what do the A transitions do? They multiply by 2 here and go back and forth. And they multiply here by 3. And the B swaps these two. And minus B here and plus. And then there should be some C. I have one out. 5C. I drew this wrong here, so there's another 5C here. Okay, this is W1. This is W2. Okay, and now my claim is that this is actually unambiguous. And let's look at the word that we had before, this AB. So what happens is that by this construction, if you read the word left to right, the transition between the components is deterministic. So the only inputs are in W1, so you must be starting here. And then if you read an A, you know you will end up in W2, because this is how we constructed it now, right? And then if you read a B, you know you're going to end up in W1. So if you have a run for AB, it's going to start here, jump into W2, and then jump back. Okay.
But somehow B from 1 prime goes both to 3 prime and 4 prime.
It should be reversed, I think. It should be for 4.
Yes, you're right, thanks. I stayed true to the transition of drawing the arrows in the wrong way. Sorry. Yes, the B always goes from W2 to W1. Right. Okay, so what we do, we read first left to right. It gives us the transitions between the components. And now you see in this component, we only have one terminal state, 1 prime. So if you have an accepting one, it must have ended in 1 prime. But now read the word right to left. Well, the last letter was a B. So in theory, we could have come from 2 prime or from 4 prime at this point. But we know that we were in W2 in the previous point, because we know how we went to through the components, right? So we know we must have come from here, from 4 prime. And now we need some A transition, and there's actually just one in this case from 2 prime. So the only run for AB is start at 2 prime, go to 4 prime, go to 1 prime, and you see this by reading the word first left to right and then right to left.
Yeah, because in this block structure is block deterministic left to right,
Yeah.
and inside each block it's backward
It's
deterministic
deterministic in the other side.
right to left.
Like co-deterministic.
So the matrix structure is this.
And well, this was definitely known before that the semi-monomer matrices give rise to unambiguous automata. This is not new, but it's nice to see in the picture, I think, how to complete this thing. And well, okay, in theory you could do this for every word, or you could write a formal proof that this actually now is unambiguous. So A prime is unambiguous. Okay. So that was kind of nice, but it worked in one example. Another theorem is that this always works if you start with something that has this arithmetic restriction. There's one thing I'm going to skip over. We didn't really talk about the choice of bases. I just took them in such a way that it worked. So if you start with some minimal linear representation, so minimal, and you have this property that all your outputs are in some, all your outputs are in some finitely generated subgroup of the field, then you can assume without loss of generality that in fact the reachability set has all entries in G0 after some choice of basis. So you can assume that u mu x star consists of vectors with entries in G naught 1 cross G. Okay, I'm not going to go into detail about this, but you need to do this base change potentially. And then the theorem is the following. So this was with Jason Bell and myself in 21. If the irrational series is Boyer, and that just means this condition, then if you construct A hat in this way and choose the right basis, then A hat is unambiguous. So if there is an unambiguous automaton recognizing a series, this construction will produce it. And it sort of leads to an algorithm in that, okay, this base change is, so you can minimize, you can do this base change, and then you need to figure out the linear hull. This is the difficult part. So you need to compute this closure, but this is computable. I'll say something about this later. Yeah. I'll say this later. And then you just construct this automaton, and then you check if it has the semi-monomial shape. If it does, okay, you have produced an unambiguous automaton. If it does not, you know there is none. Okay. But what we have done now, we've done this construction, and we have not really seen that if there's some unambiguous one, this one will give it. So there was this, we had this nice structure on the matrices, and this block structure is just forced by how we choose the transitions between the components of the linear hull. This was just some linear algebra. But now this magic thing happened that in each column of each block, I have at most one non-zero entry. So in the example, this just happened, okay? And we need to prove that if your thing is unambigualizable, then this always happens. And this is where the second tool comes in, the very big hammer. So let me erase this here. These are discriminant equations. And it seems I do have enough time to show how this works. So why does this work? These are unit equations. So this is some theorem equations from Diophantine number theory. This was proved, I think, in the 70s or 80s, independently by Evertse and van der Voort and Schlickerwey. And this is actually quite a deep theorem, but the statement is easy. So we have a finitely generated subgroup of a field, as we had before. And now we're just solving a homogeneous linear equation. So we are looking at solutions of some equation of the form a1 x1 plus a an x is 0. And let's take all coefficients non-zero. Okay, if I just care about solutions of these equations, I'm doing linear algebra 1, first semester stuff, but I want the solutions to have entries in G. So I'm solving this with all xi's in G in this finitely generated.
AIs are also in G or
That doesn't matter. Because you can just make
they
the
may be in G or they may be in what, in K?
in K for sure, but it doesn't matter, you can just add them to G. So you can assume that the AIs are in G. But that is irrelevant here. You can also make them all 1 and the field value doesn't change. So let's just take them in K. Okay, and then the claim is that somehow there are more or less only finitely many solutions, but this cannot be true in a strict sense. This is a homogeneous equation. If I have one solution and I take some element from G and multiply the whole vector by G, I get another solution. So I must count them projectively.
So you wrote it's not, so AI are not in K but K power X?
Well, sorry, this should be at times. I'm
What
taking
is
a
X?
non-zero here.
What's X then?
K
Non-zero.
the units of
The units of the field. The K times,
So AI is in K or in K power X?
it's in K.
Okay, okay.
The X here is the times, backslash times in Artig. So I'm just taking non-zero coefficients.
Sorry.
So-
K, so you have this notation which I read K power X, but maybe I read
No,
it
no,
wrong.
this is not power X.
what is
These
that?
are the units of the field, the non-zero elements of the field.
Okay.
So in the field, everything but the zero has a multiplicative inverse. And
Okay,
this is just the field minus zero.
Okay. Yes.
And this, yeah, it looks like an X, of course, here, but this is a backslash times advantage.
Mm-hmm.
It would be better on the slides.
Okay.
Uniform character.
Okay, some people write K star. Okay, so the first thing is if you have some solution, if x1, no, little x's, xn is a solution of star with the xi in G, then you can take some other G in G, and then this vector gx1, the gxn, is trivially also a solution of star. So you're going to have infinitely many, and you count them only up to scalar multiples, projectively. Okay? And the other thing that can happen is something similar, but now some subsum here could be equal to 0 for some solution. Then the other subsum is also going to be equal to 0. And then you can rescale the first components with one scalar and the other components with another scalar, and it's going to stay 0 because the subsums are already 0. So if there is a proper subset of the indices such that the sum of AIXI is already 0 for this proper subset, then also the other sum is 0. Then the sum I not in I, AIXI is also 0. And you can rescale them independently by two things, and we call this a degenerate solution. Okay, and then the main claim of the theorem is up to scalar multiples, there are only finitely many non-degenerate solutions. The theorem up to scalar multiples.
Solution is degenerate if it's 0 on some coordinates? Or
No, not the coordinate. It could be like the sum of the
if
first
it's
two is
some
0 and
sum
the
is
sum of the
zero.
other ones is
Okay.
0.
Mm-hmm.
Okay.
Do we need to move the board again?
Oh, yes. Thanks. So, up to scalar multiples, there are only finitely many solutions. By the way, this theorem is not effective. You can get, I think, a bound on the number of solutions, but not on their size. So we cannot compute them. In G, which is where we're solving things. And the strategy for this thing is, well, up to scalar multiples, you only have finitely many things, except for the degenerate ones. But if you have degenerate ones, it's going to solve some shorter equation. So you try to do some sort of induction or something, and that's how you apply this thing. Okay. But it will actually turn out that in our setting, our topology is tailor-made to deal with this stuff.
Sorry, the finite bound, is it computable, small, big?
The number of solutions is computable, I think, but you can't bound the height. So this is famously an ineffective theorem. You cannot compute all the solutions. You can get some bound on the number of solutions, but it's useless to compute the solutions because you never know if you found all of them. Yeah, so you can prove Skolemann-Lech from this, and you can prove this from Schmidt's subspace theorem. So this is how it goes sort of in this hierarchy. But just this by itself is already deep.
I have a question, probably a stupid one. If you represent elements of GS vectors instead of exponents, right? Then these non-degenerate solutions, they are upward closed as a subset of vectors, right? Like
The
this
upward
Cauchy multiplication.
closed is a product.
It's
No, a product of two solutions.
No, I see.
No, just by so they're closed under race. So
The negative exponent is a group. Okay. I see. Okay.
So it's if you look in projective space, there are finitely many points that solve it on G. Plus the stuff that's it's degenerate is who should lie on some subhyperplanes or something like this. So you get the solutions. Okay, they're in smaller subspaces and then there are finitely many points. Okay, we have that. We want to apply this to our setting. So maybe this is the last word I need to construct. I can use it. Okay, so we apply this to our setting. So our goal is somehow that in these new matrices we produced, in the columns of the blocks, we have at most one non-zero entry. So these columns of the blocks, they are basically some linear maps from some wi to some wj. So they take some x1 through x, let's say r, to some a1 x1 plus ar xr. And these a's are now the entries of my matrix. This is some linear map, 5x1. Now I'm going to cheat a bit. We started constructing this linear hull by taking some closure of the reachability set. And we said in the reachability set we can assume all the coordinates of entries in G0. So somewhere in the reachability set these points were dense. So you cannot cover them with a proper smaller closed set. And this is all preserved under our transformations. So you would get that if you look at those points of the reachability set, omega I, that lie in the component wi, this is still dense in our topology in wi. And this just means you cannot find a finite union of proper subspaces of wi that covers all those points. Okay? And we can make all the coordinates be in G0. Do we want anything else? And also, so this A1, X1 plus so this is the key point, maybe. This is going to be again something in the reachability set, some coordinate of a reachability set. So this is also going to be in G0. This is where our S-unit equation is coming from. Okay. And the claim that we want to show is that these coefficients AI, except possibly for one, they are 0. AI is 0 for all, but at most one I. To really put this into unit equation form, I need to bring the right side to the left. So I have something of this form: A1, X1, plus AR, XR, minus in this linear combination I just called 5x. This is 0. And well, all this, I'm going to plug in x's from the omega I. So these are going to be from G0 and this is in G0. So I have that for all vectors G in omega I, this tuple G and this linear combination, phi of G, is a solution of star. Of star, and the entries are either G or 0. So in G0. So I have a perfectly good S-unit equation with many solutions, which should sort of lead to a contradiction. Okay? And the problem is now I have to deal with degenerate solutions, right? If maybe some subsum is already 0. But what does this mean?
Just a second, what is it A1 to AR in both cases? It seems like the left-hand side is the same term minus the same term. So you call
yes, but you view this, so this is the equation. These are the indeterminates of your equation. So it is 0 because it's the same term, right? But you look at the vector like G1, GR, and then the phi of G is in the last component. And yes, this is 0 because it's a solution of the equation, right? But this is now an equation in r plus 1 variables, and these are the things we plug in for the variables. Okay, what's a degenerate solution? Well, some proper subsum of this thing needs to be 0. So there is some subset, in particular I of 1 sub r, You have to be a little bit careful. It can be all of R. It could still be degenerate right if 5 is 0, such that this sum AI, let's go GI is 0 for I. Well, but if you look at this as a linear equation, if you fix your set I, this is some linear equation of my space Wi, a non-trivial one if these coefficients are not 0, okay? So it's going to cut out the proper subspace, which means the degenerate solutions where this subsum is 0, they lie in a proper subspace. Okay? And now I do this for all possible index sets. There are only finitely many. So I can cover these degenerate solutions with a finite union of proper subspaces. In other words, with a proper closed subset. So let's you have some solutions at the di of this hyperplane, and then you take d, the union over all these sets I, di. So this is going to be a proper closed subset. You're going to ignore the ones where all the coefficients are 0 because we don't care about this. Closed subset of. Okay. Well, now the degenerate solutions are kind of annoying, but we just throw them away. And by density, whatever is left over must still be dense in Wi. Because otherwise I could cover the remaining points with a finite union of subspaces, and I can cover these points with a finite union of subspaces. This would contradict density. So by density, i.e. by construction, if you throw away this D, this is dense in Wi. Okay? And now we're in business because these solutions are all going to be non-degenerate. So now I can apply the finiteness, well, not hypothesis, but the conclusion of the theorem. So up to scalar multiples, here there are only finite many solutions left over. On the other hand, there are lots of them because this is a dense set. I cannot cover it somehow with finite union of subspaces. So we want to show that all but one of these coefficients are 0. So suppose two are non-zero. Let's say, suppose A1 and A2 are both not 0. But now, up to multiples, the solution vectors, so up to scalar multiples, there are only finitely many solution vectors, which means if I divide two coordinates, I'm getting something in a finite set. So the ratios are in a finite set. Okay, and if I have somehow the ratio of two coordinates fixed, so some constant c, bring it on the other side, and you see that this is again some linear equation. So you can cover all these points with proper subspaces, the non-degenerate solutions. But this is now a contradiction, because this should be dense in my space. But I just covered this with finitely many subspaces, proper subspaces. So this is a contradiction to density. And well, we're sort of done. So the main idea of this proof is somehow with this topology you get a dense set of points with coordinates in G0. And this will generate infinitely many solutions to an S-unit equation, infinitely many non-degenerate solutions. But this theory of S-unit equation tells you there can only be finitely many. This gives you the contradiction, unless only one of these things is one of these coefficients is non-zero. So this is how this number theory comes in here. And despite the fact that this theorem is non-effective, well, we don't really need effectiveness here. We just need this to prove that our construction works. And then for effectiveness, what we really need to do is to complete this closure. And since I'm a bit at the end of my talk, let me just spend 30 seconds to say something about this. So what you're going to close is you're actually going to close the matrix semigroup. You can do this in the classical Zariski topology, so polynomial invariance. And there the group case where everything is invertible was proven in 2005 by Derksen, Gendel, and Koren. And the general case, the semigroup case by Khuchowski, Orkney, Pui, and Worrell. And then Jason and I in 23 gave a version where we stay mostly in the linear realm. Like you can first close polynomial invariance and then get the linear ones from there, but you kind of don't want that necessarily if you want to stay in the linear realm. So we had one that stays more linear. It's a kind of bad, but whatever. And we didn't have any complexity bound. So for the group case, there's a paper I saw by Nosam, Pui, Schmitz, I guess, Hamodi, sorry, and Worrell, that show that it's done in elementary time. Okay. And what has also been done is if you know you're already in the class of polynomial ambiguous automata, to decide whether it's unambigualizable, is then in P-space. This was Yecker, Philip Mazowiecki, and David Wilson did that. And I think you're presenting it this year at Links. So there's an algorithm to do that. It's not a good one. But, well, okay, so I'm a mathematician. My two complexity classes are decidable and undecidable. So for me, it's okay. But of course, you can try to get something better out of this and establish the complexity class. I'm a bit out of time, so I'm not going to talk about this finitely ambiguous stuff. This is how you get the structure result for the unambiguous, and then you get an algorithm from that with a lot of extra work. So thanks a lot for your attention.
Any questions?
Question. It's more like a comment. It seems that this Polya condition for a series is quite strong.
Yes.
And in fact, I think it would be interesting to look at more general classes of series and see in which cases the Polya condition implies rational. So this seems to be validated in at least another case. And the question, my intuition is that in the extra level of generality of series which generalize the rational, usually you allow more addition. Okay? This is pure philosophy, okay? But the Polya condition gets rid of this aspect.
Yeah.
And therefore it would be interesting to take other, I don't know, classes, algebraic series, require the Polya condition, and maybe let's see if something survives. Or
but algebraic non-commutative series, what's that?
In the sense of weighted context-free grammars. So
okay.
Non-commuting variables. This
that would be interesting because, as we talked before, for definite, even for multivariate series, is Polya, even the Bézévin property implies that it's rational already. So as you said, this is very restrictive.
Yeah.
So this is something one could look at. It would be interesting, I think. So there are also a number of these types of results now. Also for definite or Mahler series, that some arithmetic conditions on the coefficients correspond to some structural result. Like in the Mahler series, it's based on growth. For definite, there's both this Bézévin-Polya thing, and there's also something based on growth, but it's not complete, this classification, because it's a lot harder. The idea is sort of, if the coefficients grow sufficiently slow, then you have a certain structural representation of the coefficients, and ideally you get a sort of whole hierarchy from this, if you're lucky. There have been a couple of results on this in the recent years. So it would also be interesting to push the non-commutative view of the rational ones. I've never tried that.
Any more questions?
Yes, I have a question. So concerning the computation of the linear Zariski closure, if you have X is just one matrix, then it's easy.
Very easy, just draw the normal form.
Yes.
And you can read it off the draw the normal form.
And is it possible to, do you think it's possible to use that algorithm just to obtain a way to compute the general case?
It's part of our general algorithm. So you first have to do it for one matrix, and then you look at groups of matrices. And there the idea is you sort of, the closure is then, in the classical Zariski topology, the closure is an algebraic group. Our topology picks up some lower rank stuff, but it doesn't really matter. An algebraic group is dense in it. And this has some identity component and a finite transversal. And you're sort of trying to compute this at the same time. So when you see a new matrix, first you're closing the identity component under conjugation by that and taking the closure. And then you're also trying to add it to the transversal. And then the identity component, just for dimension reasons, eventually it will terminate. It goes bigger and bigger. But the transversal, this is now where you need the burn site. So you can factor something out, and then you have a finitely generated torsion group, and you know it's finite. So this will not go on forever. This will terminate. But the whole thing is a bit finicky. You need to grow both things at the same time. You cannot first do the identity component and then the other, it seems. Okay? And this is the group case. And now what happens in the semi-group case? If you think, let's say you have some big dimensional space, and then you could have smaller dimensional subspaces and invertible elements on that. So they give rise to some idempotence in your semigroup. But the structure of this Zariski closed semigroup was already studied in the 18th by Pucha and Okninsky. And the point is somehow, okay, you can have infinitely many idempotents, but sort of there are only finitely many classes where kernels have images, so where the kernel of one intersects the image of the other, something like this. So somehow only finitely many of these matter. And the point is now you have to somehow identify this, they're not quite subgroupoids, but something like this. You have to find representatives for the finitely many that matters. You call to the group case to close this thing, and then whatever is left over are nilpotent factors, so you just need to make long enough products, and at the end everything is closed. As you can imagine, this is a mess. There are two things that you need to do. First, you need some induction on descending rank, both in the Zariski closure and in the linear Zariski closure. And then the bad thing is to identify sort of this idempotence you need. I think it may be a bit better in the Zariski case, actually. But this, in our algorithm, is something where we have no runtime bound. You notice at some point it's not closed, and then you just keep generating new elements till you find this thing. And our thing has an additional ugly thing, because in the linear Zariski closure, if you take a product and you close this thing, it's a vector space, you might suddenly pick up higher rank stuff again. So you cannot really do it by descending rank. So there's a sort of reset step. In some rank r-1, you might accidentally notice some bound is violated, therefore you did a mistake instead in rank r, you jump back up. So you go down, back up, but eventually it should terminate. Of course we didn't implement this.
Okay.
If you fix the initial and the final vector, is there anything you can say about the matrix semigroups that would guarantee determinism? Some natural conditions?
I haven't thought about this. I mean, if the matrices are all invertible, what we are basically showing in the cases that I didn't tell you, we are getting a representation where all the matrices are monomial. And this sort of thing, actually, if you start with a minimal representation, the Fourier property is sensitive to the input and output vectors, the other ones not, the higher ones. So you sort of throw this away, and then you do this thing and then you have a representation of your matrix semigroup which has monomial matrices. So in each row and column you have exactly one non-zero entry. That thing is going to be deterministic. So then the point is just then you could just say it should be deterministic even only if the input and output vector have exactly one non-zero entry or something like this. But in general, I don't know, I haven't thought about this question. This could also be interesting. Yeah, how can you vary U at V? Of course, one of the tricky things that might come up is if you start to vary the input and output vectors, it might be that suddenly you don't have a minimal representation anymore. So maybe you want to first restrict to just those where this representation stays minimal or something like this.
So I propose we take the remaining questions at lunch. Is that okay? Okay. So let's thank the speaker.